Porozova. She graduated from Peter the Great St. Petersburg Polytechnic University with theoretical physics as a major subject in 2015. Since then, she has taught several undergraduate courses on theoretical physics. Victoria got her PhD very recently in December 2020 at the IOFE Institute. Did I pronounce correct? IOFE?
IOFE, yeah, IOFE Institute. IOFE based, yeah, okay. Yeah.
Thank you. She's currently a research fellow in a joint research program between Peter the Great St. Petersburg Polytechnic University and Lomonosov Moscow State University. The title of her talk is Coherent Interaction of Light with Single Atoms and Atomic Ensembles under Quantum Degeneracy Conditions. Thank you, Victoria, to be with us today. You can start whenever you want.
But I have only 40 minutes, right? Okay. So I start broadcasting. Okay. Now you can see the first slide, right? Right? Correct?
Yes.
Okay. Okay. Hi, everyone. First of all, I want to thank you for inviting me. My today's talk is based on my PhD thesis, which I defended 1 month ago. Yeah, and you said right, I defended it at IOFE Institute. Actually, Abram Yoffe is considered as a father of Soviet or Russian physics. So yeah, it's a nice place to be defended there. So really strict, harsh, and strong physicist there. My talk is called Coherent Interaction of Light with Single Atoms and Atomic Ensembles under quantum degeneracy conditions. This research was completed at St. Petersburg Polytechnic University under the guidance of Professor Dmitry Vasilievich Kupriyanov. And now I'm working there in our lab and at Lomonosov Moscow State University at Quantum Technology Center, because we do some calculations for them right now. So my talk consists of two main parts. The goal of the first one was to construct the theory of quantum light scattering from a Bose-Einstein condensate. The aim of the second part was to develop the theory of Raman Sideband Cooling of a single atom. So chapters 2 and 3 are devoted to condensate, and chapter 4 is about Raman Sideband Cooling. Okay, so in the first review chapter, I traced the connection between the existing directions of physics of quantum information with the tasks of the present and dissertation work. Yeah, so for instance, I discuss the latest achievements in control schemes for single atoms localized in special lattices. So here you can see single atoms. It's just optical lattice performed by laser beams, and here single atoms. It's a photograph from our experimental colleagues from Moscow State University. And this technique is called optical tweezer technique, and it allows to prepare atomic arrays of various architecture. So there are single atoms in the sides of the optical lattice. Further, these atoms will be considered as elements of quantum gates. Simply quantum gates is a unitary matrix, and it is necessary to provide the optimal phase matching for some quantum computing algorithm gates, CZ or C0, based on Rydberg blockade. And the problem is that when you have your atom in an optical trap, the atom has certain temperature. So, and it has a residual translational motion in this optical trap, so which unfortunately gives us a phase uncertainty. So this phase uncertainty is deleterious for qubits operations, and that's why we're really interested in suppression of oscillatory translational motion of the atom. So in other words, we just need to cool our atom down to the ground vibrational state. That's why we need to develop this Raman Sideband Cooling protocol. We also consider the connection between ultra-cold atomic systems and optomechanics schemes. For instance, for such problems, an important effect is the absence of phonon excitations, which is called superfluidity phenomenon. As is known, this effect requires the presence of non-ideality of the Bose-Einstein condensate. So here you can see atoms inside the trap, and it's some temperature below critical temperature, atoms goes to condensate phase. So in order to take this non-ideality into account, we consider the problem from the point of view of the second quantization formalism, in which the order parameter xi plays the main role and obeys this well-known Gross-Podolsky equation. So thus, for consistent description, we decided to use the quantum theory of scattering, which gives us a sufficiently rigorous formalism. So about some motivation. Now I'll give you a little hindsight. Interest in this last problem has arisen since this state of matter was obtained in the laboratory in 1995. Formation of condensate on alkali atoms is a fundamental experimental discovery that directly confirmed the predictions of Bose and Einstein. This discovery showed that unusual optical properties of BC. BC is Bose-Einstein condensate. I know I don't need to use abbreviations, but it's just maybe just one. So yeah, first, unusual optical properties. First, this is strong light scattering in the off-resonant spectral region was observed, and in this off-resonant spectral region, an dilute atomic gas would be transparent, but in the case of Bose-Einstein condensate, it wasn't transparent. Secondly, radiation propagated not in the direction of incident electromagnetic wave as usual, but in the direction of the spatial extent of the condensate. Thus, I present the results of two different works. The first work belongs to Catholic group, the group that received the condensate for the first time, and they got Nobel Prize for it. The second work for another group with which we also worked, a group by Eugene Polzik. He's working in Europe, and in these two works, the condensate was located in different ways along, and okay, here you can't see that, but yeah, it was like this. So condensate and laser beam. So orthogonally and along incident electromagnetic wave. And nevertheless, the radiation still propagated along the lengths of condensate. Thus, in order to describe these optical properties, we decided to consistently follow the quantum theory of scattering, because we can do that. Like our atom is a non-relativistic object, by photon is a relativistic object, so we can do that. And we can use quantum electrodynamics here. And we used T-matrix formalism, which is actually related to S-matrix formalism, but for these tasks which involved atom and photons, they usually use T-matrix formalism, because actually first it was used by not Cantanucci, but Cantanucci has actually two big books about that. So yeah, and he's a theoretical physicist, and he got Nobel Prize for this work in this area about atoms and photons interaction. So we use this formalism, and so problem statement is what I was considering: a single photon scattered by an atomic gas in a quantum degenerate state. So single excitation going through BC. So here you can see the interaction operator, which I use, is written in the dipole approximation, where the indices n and m correspond to the excited and ground state correspondingly. Index mu is the photon polarization index. It is the operator of the electric field. The key element of the calculation is green function. As you can see, it's connected with a D matrix element. So yeah, but I need to calculate this green function. And we call it polariton because it describes the state, which is superposition between matter and photon. This green function is represented as a time-ordered product of Heisenberg operators averaged over the state of the field system, so field system in a vacuum state, and over the state of the condensate, in which we have n-1 particles. At the same time, all operators are addressed in the interaction process. We applied the invariant perturbation theory, the expansion of the evolution operator, and the summation of the series using this famous Feynman diagram technique. So after doing that, we obtain a closed system of graphical equation. This is, I am actually really proud of this result, because yeah, if I just use the coherent state of light, not one single photon, I think we wouldn't get this closed system, but we got it. In case of a single photon, we can close it. So, and then we can solve it. In this system, double line refers to our desired propagator, that green function, which I need to calculate, and the vertical arrows correspond to the state when the atom out or into condensate. The double wavy lane is the dressed field propagator. That is the photon dressed in interaction with the environment. Environment is BC for us. And incomplete propagator, I call it this one, it's incomplete green function with index gamma. This green function corresponds to spontaneous losses in this system, which means that the atom drifts into the non-condensate phase. So we also take into account these spontaneous losses, and yeah. So to be noted that for this condensate task, we considered two-level atoms, which might be quite realistic because such a transition can be found in a really in a existing rubidium atom, rubidium atom. And the transition between S and P sublevels of the fine structure. Then, excluding the auxiliary equations, and in the approximation of weak spatial inhomogeneity of the medium, this system of graphical equations can be solved. Fortunately, can be solved, and we obtain such a complicated integral differential equations, which we subsequently solved analytically and numerically in some approximations. Here you can see the self-energy part of this, and it's like kernel, and and the self-energy part, and differential operator, and integral operator. So yeah, it's really quite difficult equations. So first, for a start, we solve this equation in the approximation of an infinite homogeneous medium. The solution gave us a visual interpretation of the excitation propagating in the form of a polariton, which is, as I said, superposition state of matter and photon. And actually, it's important to say that that we had a lot of works about this process, but only one work was close to our opinion about this process. This work was written by David Politzer. David Politzer actually took a Nobel Prize for discovery of I forgot how it called in English. Okay, he got Nobel Prize in elementary particles physics. Yeah, it's about asymptotical behavior for quarks, I guess. Yeah, like they are they go closer and they behave as a ideal gas. So yeah, but David Politzer wrote one short paper in 1991. So before actually we discovered these unusual optical properties. That article said that when you have a light or photon as an incident electromagnetic wave on BC condensate, you have a superposition state between matter and photon. So, but he didn't develop a theory as we did. He didn't derive like full consistent theory. So, but yeah, he sort of predicted. This effect. So yeah, and this polariton mode generated at the edges of the sample and far from atomic resonance had a dispersion dependence close to the photonic one and could propagate in different directions, which is responsible for the possibility of strong coherent scattering. About strong coherent scattering, actually, I have next part. So the third chapter is devoted to consideration of one-dimensional scattering problem. So we solved that difficult integral differential equation in approximation of one-dimensional scattering problem. So here, the key parameters for us is transmission, reflection, losses coefficients, and they are related with the T matrix and S matrix elements, as you can see here, right? So yeah, so now we have atoms confined to a layer. That's why we call it one-dimensional scattering problem. So and solving it. Sorry, I need to close my window because I'm sorry. Okay, so solving it for a uniform distribution of the density of atoms in the condensate phase, we actually obtain a perfect pointwise coincidence of two independent calculations. The first one was actually our calculations with quantum field theory and with applying that quantum electrodynamics. And but the second one is like the task from Landau-Lifshitz book, which every third-year student can solve for like one evening. So this the result of these Maxwell equations. So it's a classical solution, but we have a dielectric permittivity which we calculated from those graphical equations, and we just substituted it here. And so we have similar common stuff, dielectric permittivity, and we have in case of uniform distribution we have like pointwise coincidence, and I think there is really important result. So it means that such an excellent coincidence of two independent rounds of calculations clearly indicates that for light scattering from an ensemble of atoms with the uniform density distributions, the optical response of the system is insensitive to either the classical or quantum nature of statistical averaging. Yeah, that's actually quite unusual because we didn't expect that. Because first, when we started, we were thinking that we will find a difference between Maxwell's equations solution and between our rigorous quantum calculations. So yeah, it was first feeling of surprise, but then we start thinking, and yeah, so we still want to find how can we get strong coherent scattering back from condensate in off-resonant region. So we actually put this uniform inhomogeneous density distributions, which actually pretty usual because in trapping potentials, mostly condensate has this form. And as you can see, it's a physically understandable result. The reflection from smooth boundaries several orders of magnitude weaker than in the previous case of sharp boundaries. But the picture changes dramatically when we begin to consider the internal movement of the fragments as like that. So we sort of have like two clouds of BC, and they are propagating through each other, and then they are overlapping, and we have this interference, quantum interference of matter waves, which is possible only for condensate. So it's not possible for usual gas, usual gas. So in this case, the interference generates such a special periodic structure of matter, and on such periodic structure, light is scattered in a way that a characteristic beating appears. In resonance, this result can be considered as the phenomenon of Bragg-Wolf diffraction by specially ordered periodic structures. And here, the same calculation was done, but for zero detuning. So, like in this point, the zero detuning from atomic resonance. So I'm in atomic resonance here, and however, but here reflection coefficient is a function of wave number, which is simply the phase in the order parameter here. So it's sort of velocity of this counter-propagating fragments. Yeah, so you can see the maxima of Bragg's positive interference here, and it was interesting to discover the following phenomena. For the permittivity, the real part of which is actually this okay, yeah, so interesting phenomena was discovered about photonic crystal. So when permittivity has a real part close to 1, which means almost vacuum state, however, the imaginary part is oscillating, and we saw the formation of a structure similar to photonic crystal. Two polariton modes are formed. One propagates with a positive group velocity, and another with a negative one. When they collide, they form an overlap. In this case, the zones will be formed for a sufficiently extended sample. Unfortunately for our sample wasn't long enough, so we didn't see this second branch, the appearance of this second branch, because the energy between these two branches greater than gamma, much greater than gamma, and as you can see, we have this detuning in units of gamma. So yeah, if we could go further, we will definitely see this zones, the formation of these zones. It was actually pretty unusual to see. So okay, I think I finished with gamma is a rate of spontaneous decay for that rubidium atom. So the first chapter is devoted to the development of the theory of Raman Sideband Cooling of a single atom in an optical dipole trap. Actually, this problem has a long history. In fact, this protocol was used most often for ions, but we were inspired by the work of Kaufman, and these are excellent experimental works in which this protocol was implemented. Their work was okay. I actually need to say this something two words. Like when I was a PhD student, we started working on that Bose-Einstein condensate task, which was clearly a 100% fundamental theoretical work for us, because we didn't have experiment to do experiments which were, yeah, so we just did a theoretical part. But then we got some grants and we collaborated with our experimental colleagues. So we have big laboratory in Moscow now, and they wanted to do quantum computer on neutral atoms, and they doing now quantum computational gates on Rydberg atoms, which I'm working on now. But for this, actually, we need to we need to do some prevential calculations about cooling mechanism. The cooler your atom is, the better for your quantum computational mechanisms and protocols. So yeah, we were inspired by this work, but it was experimental, and they cooled atom in a three-dimensional case, but not simultaneously in three-dimensional axis, but they just did for X, Y, and then that axis. So yeah, and our idea was how to do it simultaneously. So we were seeking for symmetrical or ideal optimal geometry and other optimal conditions. So and also the work was experimental, and we wanted to develop rigorous theory. So the concept of this Raman Sideband Cooling protocol is used when the motion of the atom is strictly limited by the confining potential, which is in one good approximation, you can think that it's harmonical potential well. And the essence of the protocol is the sequential application of Raman scattering, red arrows, and then optical pumping cycles, green dashes. By repeating this, like you have an atom on this certain spin state and vibrational state, then you repopulate atom, and you lowering his vibrational state, like by reducing vibrational number on one, like -1, and you have you get entanglement spin superposition of spin states here. Then you switch on optical pumping, which doesn't touch your vibrational states because we are working at lamp decay regime, and you're just repeating these cycles. So until you will get this dark state where you know exactly where atom is, like certain spin states. Mostly it's like like for Rubidium 87, it's total angular momentum, for instance, 2, and its projection m with index f is 0, so-called clock transition. So, and you know exactly this spin state, and your vibrational numbers all are 0. So atom on a ground state, it means that atom is cooled, which we need to do. And yeah, so we prove that it can be performed by, we just did density matrix transformations by applying this process, Raman process and optical pumping, and then when we did it like many times, it's a sort of theorem, so we can get this pure state of system. See, it's a pure state, so yeah, when we can write density matrix in this form, it's called pure state. And we discovered they spin states should be mutually orthogonal for optimal regime. So why do we need that? Why do we need to have spin states to be orthogonal? Actually, if the orthogonality is not satisfied, for instance, how in this case, such superposition states arise between vibrational modes, which leads to resonance, and they are unnecessary for us because they are this is a deleterious effect for us. But it is actually worth noting that orthogonality is important and ideal, but even if these spin states are linear independent, this will already be sufficient for the optimal regime. So as I said, the task was to find the optimal geometry of laser beams, because if we decide to cool atom, atom in all three-dimensional directions, it means that we need to apply 4 beams, because one beam has modes with indices 0, like wave vector key 0, and omega 0, which is frequency for this impulse. It excites the atom. Like just through it, excites the atom, and then you're applying three other beams. Each every beam is for instance, x direction, y direction, and z direction. So your atom gets recall momentum, and voila, you have a -1 vibrational number. So, and then you just need to repeat. But yeah, so three other beams transfer the atom to the desired state in such a way that the atom receives a recall momentum along each of other traps coordinate axes, like x, y, and z. In this case, all four beams cannot be directly mutually orthogonally. They cannot be like, yeah. And we calculated the certain angles. We found that four beams should be directed along the bisectors of the main and three adjacent octants of the trapping potential of the trap. And it's important to note that these beams must be linear polarized and have mutually orthogonal polarization. So wave vectors are not mutually orthogonal, but their polarizations are. And you can just solve it, and then considering it, you can go to solve Schrödinger equation. So the population dynamics of a single atom in a dipole trap also was described by Schrödinger equation. Of course, I didn't write it because why? Yes, I just write the Schrödinger equation in energy representation for amplitude, which correspond to repopulation dynamics. And the operator of interaction looks like this, where omega is Rabi frequency. So yeah, here I just here the states, like spin state and vibrational state. Yeah. So actually, this entire system looks a bit cumbersome. So I didn't give the entire system here, but I identify this isolated transition, which is responsible for the Raman transition, because we see like 1, 0, which means that we will give recoil momentum in x direction, and the same for other indices. So we just found the crucial requirements. So light beams should be directed along octant bisectors, mutually orthogonally polarized. And also we have this not actually simple identity for reduced Rabi frequencies. There be these conditions where eta is a Lambda-Dicker parameter. We have it actually here, this Lambda-Dicker parameter. I also show it on this slide. It's Lambda-Dicker parameter, a really important parameter. So unfortunately, we can't find one parameter to do optimal ideal Raman Sideband cooling process, but we have a set of requirements. And also we need to minimize the leakage. Leakage is a process when your atom populates the states with unchanged vibrational number. So results, here you can see calculation results. We took the Rubidium 85, and if in my first part about condensate I took model atoms, like 2-level atoms, here I consider real atoms with a real fine and hyperfine structure, and I'm considering clock transition and detuning -1000 gamma and temperature 20 microkelvin. So this is detuning from the excited state. Yeah, and this temperature actually corresponds the average vibrational numbers for radial motion 2 and 4 for axial longitudinal motion, I mean in direction of z-axis. So upper plot, time, you can see time dependence of the occupation probabilities for the destination states green solid curves, and for base states when you have from 0 time you have atom here, and then atom repopulates into these states. And yeah, it is into the state where your vibrational number -1. Yeah, so it's a destination state. Also, you can see these satellite gray curves. They mean that they show the bounds of its possible variation within one standard deviation from the mean values. It means that we just calculated not for mean value of vibrational number, like for instance 2. We also calculated for vibrational numbers with one standard deviation. And all functions demonstrate periodic dependence, and the system evolves to the destination state at the extremal points. It can be seen that there is a tendency after some time tau, which is approximately equal to 0.2 milliseconds, this system populates into the destination state we need. And lower plot show you imperfection and leakage. Leakage is a process when you populate in states where your vibrational number is not changed, but imperfection means that you can actually populate these adjacent states. So this is imperfection if you're here. And yeah, so we also calculated it, and it has amplitude less than 1%. So it actually makes a small contribution, and leakage also has a small amplitude. So as I said, leakage, I didn't say that, but yeah, I'm saying that now. Leakage has a strong oscillatory behavior, which is due to the weak coherent coupling of the base state with states of the M+ group, which is M+ group, with the vibrational quantum number not reduced by 1. So actually, it's sort of all. And here we have some requirements for our PhD thesis. We need to have statements which I need to define. So I defined 4 statements. Like my main results of my PhD thesis. First is I discovered that light scattering from Bose-Einstein special oscillations is similar to the Bragg diffraction phenomena, and the feature of the process is the possibility of strong coherent scattering even at a low atomic density in the sample. 2. Bose-Einstein condensate in the process of fragmentations forms an inhomogeneous special structure with periodic oscillations of the order parameter and atomic density, which leads to special modulation of the BC permittivity, forming an optical medium similar to a photonic crystal. 3. The three-dimensional realization of the Raman Sideband Cooling needs quantum entanglement between the spin and vibrational degrees of freedom of the trapped atom. And 4. Optimal conditions for Raman Sideband Cooling are the symmetric geometry for 4 light beams in the direction of the dipole trap, as well as matching the intensities, and intensities is connected with reduced Rabi frequency, so it's sort of the same, and polarizations of optical modes that control the cooling process. Yeah, okay, it's 37 minutes. This is my publication. It's not all my publication, but related to my PhD thesis research. And first one was in 2016. It's about that polariton mode. And second one is we developed our theory here, and about Bragg diffraction, where we found out this photonic crystal behavior. And the last one is about Raman Sideband Cooling mechanism, which we developed for our experimentalists. Thank you for your attention. So I'm done.
Thank you very much, Victoria. I don't know if the audience has questions.
Okay. You can say a number of slides and I can go there. Okay. Okay, I just don't hear any questions. Okay.
I think it was very clear, I guess. No questions.
No questions, really. Okay. Yeah, I actually, it's understandable because it's like fast review, but most often questions I got if it was about what was the, because I was defended between semiconductor physicists, and they just asking me like all the time about the difference between this periodic structure in BC and quantum dots, and yeah, so and they say, yeah, we already discovered this the theory there 15 years ago and so on, but yeah, so it was like most often asked question for frequently asked question for BC part. And about Raman Sideband Cooling, I can say that like if you want to like more detail like for seminar discussion, so I need to just take more narrow parts so we can go through maybe some equations or something like that, I don't know, but we did it for our experimental colleagues, and when we found this symmetric geometry, they said that they can't do that in real life. And that was my disappointment about that, but yeah, I think we still need to do it, but maybe for two-dimensional case.
I have a very basic question.
Okay.
Why rubidium? The
Why
element
what?
that why rubidium? Why
Why
did you take?
rubidium? Why
Yes.
rubidium? Because for these experiments, rubidium has a quite resolved hyperfine structure and really convenient parameters to implement these operations on rubidium. It's really convenient. It's like rubidium, or maybe it's Celsi. I don't know how you call it. Like mostly it's about rubidium. Yeah, it's like really good hyperfine structure. But yesterday I was talking with my colleague from UK, and he said that they are doing atomic interferometer for maybe gravitation waves observation, and he said that they want to use strontium, not rubidium. That strontium is better. That's why, I don't know, just like, yeah.
Okay.
Another question. Yeah.
Could you talk a bit more about the polariton and how
Yeah.
is it related to the polaron?
So about polariton and how what?
How is it related to the well-known polaron?
No polaron. How is it related to non-polar?
Well, there's this polaron that Feynman invented, yeah?
Mm-hmm.
Now you introduce some polariton here, yeah?
Mm-hmm.
Could you explain a bit more what it is?
Okay, so polaron is a quasi-particle in crystal, right? And it consists of it's a quasi-particle using condensed matter physics and electrons and solid materials. Yeah, but actually, I think it's pretty similar. But it's like they used to say that when you have first, we don't have crystal here. It's not solid state, it's gas here. So, and we have photon propagating through gas, almost in a vacuum state actually, but in condensate phase, which is important for us. And then this superposition between excited atom, which goes in and out condensate, and photon, and this superposition is propagating through this, and we call it polariton. So yeah, so that's my answer.
Yeah, but is it in some sense an eigenstate of propagation?
Also, they said that polaron is a sort of fermionic quasi-particle, right? Fermionic quasi-particle. And in our case, we have a bosonic quasi-particle, but I don't know how important it is. Maybe, yeah. So what was the question? The second one.
Can you define it by, let's say, diagonalization of a dispersion relation?
Yes, we got a dispersion relation. I actually can show you. Yeah, 1, 2, 3, 1. It is here. 1 second. Here. So for your polariton, you have atomic type dispersion relation. Here it's a Lorentz shift, and shift which is caused by spontaneous losses. And so yeah, and here it's a photonic dispersion. So when you're at resonance, you have atomic type of resonance, and then, for instance, you go far off atomic resonance, and another branch, another part of this polariton just appears. It is photonic type, so just omega ck. Yeah, that's how it's propagating. It's one of the favorite results of this theory. Yeah. So for dilute gas, you won't get this branch, but for this you got it. Yeah.
And does it come out of a fully relativistic calculation?
For relativistic, you mean relativistic calculation? You mean applying quantum electrodynamics tools?
Well, you say you're applying quantum electrodynamics, but
yeah, we applied it here, because of course your atom is not relativistic, but your photon is relativistic particle, so you can apply it. Most usually you have a G for interaction operator, but an integral, blah blah blah. But for in dipole approximations, which all people use for atomic medium, you can use this form of notation, and here you just do evolution, operator expansion, summation of series of this perturbation theory. I just didn't give you that because it's a large, a lot of pages, but yeah, so you just get a lot of series, and then you do summation, and this equation is integral differential equation. These are two, and I just opened it. I mean, I just rewrite it in a normal view, like with integrals. It's in a Fourier transform representation, and there I just solved them. So I first solved these equations, then substituted these equations. This gamma green function with gamma gave me dielectric permittivity, which is responsible for losses, and and then I just substitute the solution here, because here you can see in your main equation you have this line. So yeah, that's how we just use formulas of S matrix here. We can do that for this physics system. We can do that. Yeah.
But for the system to close, you probably had to make some kind of approximation.
Yeah, we did approximation. So first approximation was that weak, like we have inhomogeneity, but like a weak inhomogeneity process. Like So you mean to get this equation or that, or further?
just to get a closed system of equation.
To get this system equation. Yes, that's a. Yes, I guess it's just only one, like first dipole approximation, like it's a starting point, it's a first and the main one, and probably then, and I think maybe that's all. And then we just, when we were solving these equations to get this equation, we did another one. But yeah, for this system, only dipole approximation. That's all.
Okay. Very interesting. Thank you.
Thank you.
Thank you. We have a question on the chat. Baiwa asked, how can we predict row weight?
What means raw waves? What does it mean?
I don't know.
Me too. Raw waves. I mean, I know what means the adjective raw, but maybe he meant waves like meta waves. Actually, if it's about meta waves, so actually people observed it okay, I didn't show it, but yeah, in experiments we have this just interference between the two Bose-Einstein condensate fragments, and this oscillatory behavior, it just first was observed in experiment, and then you can solve Gross-Piatkowski equation in Thomas Fermi approximation, and one of the solutions can be like this. So it gives you this interference pattern. That's how. If it is about this, it's Thomas Fermi approximations of for Gross-Piatkowski equation for solution of this equation. An experiment, you just forcing these two clouds propagating through each other, and then you just do some photographs on absorption images, and you can observe these peaks, maxima and minima, and yeah, so you can see this interference pattern. It proves that Bose-Einstein condensate actually has this meta wave nature. One of the most important result here, because in case of Bose-Einstein condensate, you can have almost zero, almost not zero, but close to zero density of atoms, and still you get this strong coherent scattering. But we compared it with atoms, and you can locate atoms as a periodic structure, but you need to take a lot of atoms to do that. It's about much larger density. So yeah, that's the main difference here. Okay, maybe another question.
Thank you, Victoria.
So, rubidium was used in an experiment to create sonic black holes. Any correlation to it?
Okay, so you're asking about Bose-Einstein condensate.
Yeah, yes.
To like in application to like model dark black holes. Actually, I was reading some articles, but like a bit, because it sounds pretty interesting for me. So and we have this phenomena. I forgot the name, but you have this phenomena when all atoms just put one state. You can observe this something really similar to like singularity. Yeah.
Yes,
So
yes.
we didn't do that, but maybe if I but it sounds interesting. So yeah, I think people did something here, but yeah.
So they created a sonic black hole. It absorbs all the sound waves using it, So that is why I was asking that why rubidium? Is it so the experiment that you did has does it have any correlation to it?
Our
Because it is also based on Bose-Einstein BC thing, and your work is also on that same thing. So that is why I was asking.
Yeah, I know, but I guess it's sort of different experiment because our part was clearly optical part. We didn't consider atomic part of our task. We only put this Xi order parameter there in our equation, but as you saw, we found optical characteristics like transmission reflection coefficient. So we solved optical part of that task. You said sonic, which means probably sound waves or something, right? Like phonons,
Yes,
maybe.
yes.
Yeah, so we didn't do phonons, but I think it's like Bose-Einstein condensate a very interesting subject to research. Maybe one day I will do something like related to black holes and creating these model black holes. But yeah, but we didn't have this correlation with what you asked. But yeah, it's probably.
Not from a physics background, just enthusiastic. So I keep reading. That is why I asked.
Thank you. Yeah, that's interesting. I know. I agree.
Okay. I think we have no more questions. So we thank Victoria again.
Emilia, I
With
can't
us.
see you. You turned off your camera.
Oh yeah, sorry.
Oh. Okay. Okay. Yeah. Now it's better. Yeah.
So, thank you very much, Victoria.
Thanks.
Okay. Thank you. Thank you.
Thank you very
Thank
much.
you.
Thank you, guys.
It was nice. Bye bye.
Have a
Thank
okay.
you.
Have a nice
Ciao.
day. Yeah.
Thanks.
I'm working.